main objective of this program is to sort a set of elements in a 1D array using insertion sorting principle. We wanted in this example array to be sorted in ascending order. The main theme is as follows. We take elements starting from the second element onwards. For example, second element means index is 1, I value is 1. So if we wanted to say that the elements till I value I, that is till 1, if they are supposed to be called as in sorted fashion, means all the elements before I, they should be smaller than the element at location I. Otherwise they are not sorted. Rather, in the insertion sorting, we try to see that we take ith element and compare with all the elements before it. If we find the ith element value is smaller than any of the elements before it, we move the elements above this ith element value by 1 unit right, and then we will insert the ith element such a way that all the elements will be now sorted fashion. This is the main essence behind this insertion sorting. That is, we are going to take one element, say ith element, and then we are trying to insert the same at its appropriate place such that the elements till that ith location, all of them are in the sorted fashion. This is repeated for all the elements of the array such that total array gets sorted. The code is given in the slide. The simulation is following. Let us consider the array is having elements 1, 9, 6, 4, 15, 8. We will start from second element onwards, that is I is equal to 1 onwards. For example, in this case, ith element, when I value is 1, ith element value we are taking it as a key. Key value is 9. We will compare this with all the elements before that, before I. So incidentally in this example, there is only one element. Its value is also 1. As that 1 is also less than 9, which means that the array is already in ascending order till I. Thus we do nothing. Now I value is incremented by 1, that is 2. We have to compare the second element, its value is 6, with all the elements before this. Thus the for loop for j is equal to 0, j less than I will be working. We start from 0th element and we will check for the existence of any element whose value is greater than the 6 in this case. If it is so, we are supposed to insert 6 before it. To insert before 6, we have to move those elements, and then we have to insert. Let us see what happens. Now key value is 6. That is a of I is 2, so a of I is 6. We wanted to insert 6 at its portion, at its appropriate place, such a way that all the elements till second element, or rather I say index 2 till that element, till that element, till that location, the elements has to be in sorted order. J value is 0. A of j, that is 1. Is it greater than key? Rather key, is it less than a of j 1? No. Thus the control goes to the next iteration of this for loop. Now j value is 1. A of j 9. Key, is it less than 9? Yes. Thus the key value, that is 6, it has to be inserted before this 9. To do this, we have to move 9 by 1 unit, and then we have to insert 6 there. For this, the for loop for k is equal to I minus 1, k greater than equal to j, k minus minus a of k plus 1 is equal to a of k will be executed. That is, k is equal to I minus 1. I value is 2, 2 minus 1, 1. K is greater than equal to j? Yes. Thus, a of a k plus 1 is equal to a of k. That is, a of k 9 is moved to a 2. Thus, in place of 6, 9 will come. Now the key value is stored in a of j. J value is 1. A of j is equal to key, that is 6 is now stored in the a of 1. Now if you see the elements 1, 6, 9, they are in ascending order. Now I will become increment by 1, it becomes 3. Thus we are interested in finalizing or inserting a of 3, that is 4, into the array such that the resultant array will be again in the ascending order. For this purpose, again the for loop for j is equal to 0, j less than I, j plus plus will be executed. J value is 0, a of j 1, is key less than 1, that is 4, is it less than 1? No. J value is now 1, a of j, that is 6. Key, is it less than 6? Yes. Thus, we are supposed to insert 4 before 6. For doing this, we have to move the element 9 by 1 unit, right? And then 6 by 1 unit, right? And then 4 can be inserted. For doing this, the for loop for k is equal to 0, k is equal to I minus 1, k greater than equal to j, k minus minus will be executed. Starting value of k is 2, that is I minus 1. Thus, a of k plus 1 is equal to ak is executed. That is 9 is moved to a of 3. K value becomes 1. A of k, that is 6, it will be moved to A of 2. A of j is equal to key is executed. That is, key value 4 is stored in A of 1. The elements till third element of the array, they are in ascending order. That is 1, 4, 6, 9. Like this, we are taking one element and we are inserting at its appropriate place such that the array gets into ascending order till that location, that is ith element, till that ith element. I value is incremented by 1, thus I value becomes 4. A of 4, that is 15. Now we are interested to find out whether 15 is required to be inserted somewhere or not. For doing this, key value will be taken as 15 and then all the elements before I, they are compared against 15. Incidentally, in this example, all the elements 1, 4, 6, 9, they are smaller than 15. Thus, 15 location is not required to be changed. Now I value will be incremented by 1. I value becomes 5. A of 5, that is 8. We are interested to find out where the 8 has to be inserted such that the total array elements will be in the ascending order. For doing this, we have to compare as usual with all the elements before I. Key value will be taken as 8. The j for loop will be executed. J initial value is 0. A of j 1. Is it greater than 8? No. Thus, the control goes to the next for loop of this for loop. Now j value is 1. A of j, that is 4. Is it greater than 8? No. Thus control goes to next iteration. Now j value is 2. A of j, that is 6. Is it greater than 8? No. Thus control goes to next iteration. Now j value is 3. A of 3, that is 9. 9, is it greater than 8? Rather 8, is it less than 9? Yes. Thus 8 has to be inserted before 9. Before doing this, we have to move 15 by 1 unit, 9 by 1 unit. For doing this, the k for loop will be executed. Initial value of k is taken as I minus 1, that is 5 minus 1, 4. A of k plus 1 is equal to A of k is executed. Thus, 15 is stored in A of k plus 1. K value is 4. So, A of 5 becomes 15. K value will be reduced by 1. K value becomes 3. A of k plus 1 is equal to A of k is executed. That is, k value is 3. So, thus A of 4 becomes A of 3. That is, 9 will be stored in the A of 4. Thus 9 will be moved by 1 unit towards right. Now the statement A of j is equal to key is executed. Thus 8 will be stored in A of j, that is A of 3. Now all the elements 1, 4, 6, 8, 9, 15, they are in the ascending order. Like this, the basic theme behind the insertion sorting is we take one element and compare with all the elements before it and identify where this has to be inserted. Before insertion, remove or rather I say move the elements by right one unit and then insert this new element such that the resulting array till that point will be in the ascending order. This is the theme behind the insertion sorting principle. Let us try to have another version of the insertion sorting compared to the previous program. Here, simple modification is done. In the previous solution, we compare the key element with the previous elements and find out the element whose value is greater than the key element and try to insert the key element before that by moving those elements whose values are greater than key element. Here, instead of doing that, we compare the key element with the previous element. If the key element is less than the previous element, exchange them. This we repeat till we find a element whose value is less than the key element or there are no more elements to be compared. In the following slides, we will try to simulate this version. Conceptually, both the algorithms are same. Just for the sake of explanation, we are taking some set of values. However, visually we are displaying them as bars to show the visual way how the sorting takes place. The height of the bar indicates the value. Higher the bar height, higher the value. We take the second bar. Remember, I is equal to 1. That is the, when you see, that is the index of the second bar that we are taking. And we have to compare with the previous bars and place this one at its appropriate place. Rather, in this implementation, what we propose is we compare this bar with the previous bar height, and if this is smaller than the previous bar, we will exchange them. We will proceed that in that direction till there are no more bars to compare or we find a bar whose value, whose height is less than this. As the height of the first bar is less than the second bar, we need not require to exchange them, which indicates that the second bar which we have selected to identify to check whether is it more than all the bars heights before it or not. So we found that it is larger than the bars before it, the values before it. So we keep quiet. We keep that one at the same place. Thus, those two elements can be said as sorted. Like this, we proceed. Now we are taking the third bar and we try to compare its value, its height with those bars which are before it. And if this is smaller than the bars before it, we'll exchange them. This is repeated till we find a bar whose value is smaller than this bar, or till we go to the beginning of the array. Now we are taking the fourth bar and then compare its height with all the bars before it. Then do appropriate exchange operations. Now we are taking the fifth element of the array. With this also, we do the same. We compare this one with the previous values or previous bars and accordingly exchange them. Now we are taking the sixth element. With this also, we do the same. Now we consider the seventh element of the array and try to find out where it will fit in the sorted array. Now we are taking the last element of the array. Now we assume that the data is already in the ascending order. What happens when we run the insertion sorting algorithm on this data? We can see in the coming slides. You may find that already the data is in ascending order and we wanted the elements to be in ascending order. So in this situation, this algorithm shows best case performance. That is best case complexity, because we take ith element value and compare with the I minus 1th element value. Obviously, already the data is in ascending order. So the ith element value will be more than I minus 1th element. So we need not require to compare with the remaining elements before that I. So we come out like this. The algorithm complexity is order of n, where n is the number of samples. So this is the best case behavior of the insertion sorting algorithm. In the following slides, we'll demonstrate how the insertion sorting algorithm works on the data which is in the descending order. However, the algorithm wanted to put the elements in the ascending order. So you may find that the algorithm behavior is worst behavior here. That is, it takes more number of iterations. For example, if I take already array is in the descending order, which means that ith element value is smaller than the I minus 1th element value. If that is the situation, so when we try to apply the insertion sorting algorithms, when I take ith element, its value will be smaller than all the elements before it. Thus, we require to spend I minus 1 I comparisons and exchanges. It is going to for each element we have to compare with all the elements before it, and we require to exchange also. We may see in the following slides how this thing is going to take place. This is the worst case behavior of this insertion sorting algorithm. Already we have seen that the algorithm has best case behavior and worst case behavior. In the best case, that's a situation where the array elements are already in ascending order and we wanted to sort in ascending, make them in ascending order. We require hardly n minus 1 comparisons. Thus, the order of the complexity is order of n. Whereas in the case of the other situation, that is, the array elements are in the descending order and we wanted to put them in the ascending order. Thus, if we take I value is 1, first element, then the first element value is smaller than all the elements before it. How many elements are there before first element? One element is there. This is smaller than that. Thus, there will be exchange. Thus, one comparison is required. Similarly, if we take the second index element, that is the third element, as the array is in descending order, its value will be smaller than two elements before it. Obviously, we require two exchanges and comparisons. Thus, two operations are required. Like this, the order of the complexity of this algorithm becomes n into n minus 1 by 2. That is the second order complexity. There is no much difference is there in order wise, complexity wise, order of complexity wise. This is same as bubble sorting complexity.